In this video, we are going to look at 17 more problems, and we're not going to do all of these hypothesis tests, but instead we're going to focus on two key skills. The first one is, which type of hypothesis test is it? And then the second one will be, what are the null and the alternate hypotheses that go along with this hypothesis? Because with this test, because quite honestly, those are the key skills on the exam. Most people, when they know that, hey, this is a two-sample t-test that's not pooled, they know how to run it. It's determining that it's the two-sample t-test that is not pooled that is the more important skill. Also, understanding which is the alternate hypothesis is another key skill, because that can also cost you quite a few points on an exam. So this covers chapters 7, 8, 9, and 11. So all of the hypothesis tests we've learned, it's meant to be more practice prior to our final exam. So I'm hoping that you will, again, as we're watching this, pause the video and try and guess along with me, what are these different hypothesis tests and what are the hypotheses? So here we go. The first question, kind of starting off easy. The National Health and Nutrition Exam and Survey weighed a sample of 546 boys aged 6 through 11 and found out that 87 of them were overweight. They weighed a sample of 508 girls aged 6 through 11 and found that 74 of them were overweight. Can you conclude that the proportion of boys who are overweight differs from the proportion of girls who are overweight? So right off the bat, your alternate hypothesis, proportion of boys differs from the proportion of girls. And your null hypothesis would be proportion of boys equals the proportion of girls. And this is a two proportion z-test. Okay, so that's what we're going to be doing going through these problems. Now that you've got your feet wet, let's keep on going. Number 2, King Tut was an ancient Egyptian ruler whose tomb was discovered and opened in 1923. Legend has it that the archaeologists who opened the tomb were subject to a mummy's curse, which would shorten their lifespans. A team of scientists conducted an investigation of the mummy's curse. They reported that 25 people exposed to the curse had a mean lifespan of 70 years with a standard deviation of 12.4 years, while, we're misspelling, I apologize, a sample of 11 Westerners in Egypt at the time who were not exposed to the curse had a mean lifespan of 75 years with a standard deviation of 13.6 years. Assume that populations are approximately normal. I'm glad we've got that there. Can you conclude, this is usually where the key information is given to us. Can you conclude that the mean lifespan of those exposed to the mummy's curse is less than the mean of those not exposed? So mean exposed less than the mean of those not exposed. Notice how easy it was to read that out. So the null hypothesis would be, and I'm going to erase that and start over, mu of those exposed equals the mean of those not exposed. Now, which test is it? We obviously have two means, and it's not a paired set of data. So this is a two-sample t-test. But we're not quite done yet, because we need to determine whether we're going to pool the standard deviations or not. It's not about whether the sample standard deviations are the same. They aren't. It's whether the population ones are, and we don't know. And then we look at whether people were randomly assigned into one group or another. Well, that's not the case. You either were part of the archaeological team or you were just happened to be a Westerner in Egypt at the time. We did not flip a coin and say, hey, you get to be on the archaeologist team. That wouldn't be quite fair to the scientists who had been working their whole life and studying about the curse to do that. So this is definitely going to be in the not pooled category. Moving on to number 3. WeatherWise magazine is published in association with the American Meteorological Society. In volume 46, number 6, there's a rating system to classify nor'easter storms that frequently hit the New England states and can cause much damage near the ocean. All that stuff basically says, hey, we're dealing with nor'easters. It's stuff that we can just kind of ignore there. A severe storm has an average peak wave height of 16.4 feet for waves hitting the shore. Suppose that a nor'easter is in progress at this severe class rating. Let's say you want to set up a test to see if the wave action is getting worse. What would the null and alternate hypothesis be regarding the wave height? The only number we have here is 16.4 feet. And we want to know, is it getting worse? So our alternate would be mu is greater than 16.4 feet. And we would assume that if it's not getting worse, it would still be at that 16.4 feet level. Since there's just a single mean, this will be a regular t-test. Now, we couldn't even do this problem because we don't have any data. If there were data, what they'd have to do is they'd have to go to a lifeguard stand, perhaps, or the end of a pier. Someone would be there with the binoculars looking at the waves as they're coming in from a storm, and every couple seconds a new wave would be cresting, and that person would be reading off, how high the waves are, and someone would be writing them down. And if, you're probably going to take about 3 minutes, and you'll have 40 or 50 wave sets coming through, and those would be the values that you would use on this test. But we don't have that information, but we didn't need it to identify which test and what the hypotheses would be. Continuing on to number 4, the number of false fire alarms were counted each month at a number of sites. The results are given in this table. Okay, so each month is listed and the number of false alarms there. Okay, that makes sense. Test the hypothesis that the false alarms are equally likely to occur in any month. That's a little bit different. Are equally likely to occur. So we go through our checklist. We're not dealing with proportions. That's gone. And I don't see the word mean in here anywhere. So it's not a t-test or a 2-sample t-test or an ANOVA test. So that kind of leaves the chi-squared category of things. And that means, okay, is this a matrix? Well, I do have number of alarms on the left and month on the top, maybe. And then we also have a goodness of fit. And that's really what we're dealing with here, because we want to know, are they equally likely to occur? If they were equally likely to occur, we wouldn't have this, this scaling here where you have this different months where there's different, this is a very poor drawing here of all these different months, and sometimes it goes lower, etc. Instead, it would be leveled off all the way across if it were equally likely to occur, and there wouldn't be these highs and the lows. So our HO would be that the number of false alarms is equally likely or equally distributed throughout the months. And then the alternate would be it is, etc., is not equally likely. And we're trying to show that there is a preponderance of more values in some months compared with the other. So this is going to be, as I said, the chi-square goodness of fit test. Now, how would you do this? Well, you would type all these numbers in as the observed values into list 1, and then you would add them all up and divide by 12 or calculate their mean and fill that mean into all 12 in your expected value column, and then you would run the chi-square goodness of fit test. I wish there was a set of words that I could give you that says these are the words you always look for, but the English language is strange and there's no set of words that is always going to work for you. Better to understand the concepts of these problems. Number 5. USA Today reported that about 47% of the general consumer population in the United States is loyal to the auto manufacturer of their choice. Suppose that Chevrolet did a study of a random sample of 1,006 Chevrolet owners and found that 490 said that they would buy another Chevrolet. Does this indicate that the population proportion of customers loyal to Chevrolet is more than 47%? P greater than 47%. There's our alternate hypothesis, and the null hypothesis would be P equals 0.47. And which test is this? This is going to be a one proportion z-test. And I realize I'm not pausing and asking you to, stop and think on your own. So I hope that you're just doing this naturally to get the best benefit out of this review. One thing is for you to listen to me just walk you through it, but another thing is for you to stop and have to generate this on your own. And that's really where the learning occurs, when you find out that hey, I missed it, and why did I miss it? Problem number 6. Let X be a random variable that represents the milliliters of oxygen per deciliter of blood. And for healthy adults, the population mean of this variable is mu equals 19.0 milliliters per deciliter of blood. And that comes from the Merck manual. A company that sells vitamins claims that its multivitamin complex will increase, there's a keyword, the oxygen capacity of the blood. A random sample of 48 adults took the vitamin for 6 months, so it's a single sample. After blood tests, it was found that the sample mean was 20.7 with a standard deviation of 9.9. Use a 1% significance level to test the claim that the average has been increased. We're trying to see if mu is greater than the 19.0, which comes from the Merck manual. Okay, we're going to assume that it's just the same. And since we only have one sample, this is a t-test. Notice how often it's easier to go straight to the alternate hypothesis, because that's going to come straight from the problem itself. Problem number 7. A CNN poll taken in July 2012 obtained responses from 1,517 adult Americans to the question, how would you rate the economic conditions of the country today? As very good, somewhat poor, or very poor. The following table presents the results along with the proportions of people who gave these responses back in 2011. Can you conclude that the proportions of people given the various responses changed between these 2 years? Well, there's a lot of proportions, and it's hard to lock on to which one, because I'm actually seeing 4 different categories, and we don't have a 4 proportion z-test. This is actually going to be a chi-square goodness of fit test. Notice how you have numbers for one column and you have percentages or probabilities in the other column. Now, as far as the null hypothesis, you're going to say the proportions in 2012 are the same as in 2011, And then alternately, the proportions in 2012 are different from 2011. So it's a whole proportion of distributions here. So I have the proportions. To calculate the expected values, you're going to go E equals NP. Your N each time is going to be 1,517. So on this first row, you'd multiply by 0.01 for 1%. On the next row, you'd take 1517 and multiply by 0.24. And you can see what we're going to do going down. And that would generate the expected values for your second list. And then you would run the chi-square goodness of fit test. Let's move on to number 8 out of 17. A tire manufacturer is interested in testing the fuel economy for 2 different tread patterns. Treads of each tread type were driven for 1,000 miles on each of 9 cars. The mileages in miles per gallon were as follows, and you see the data over at the right side of your screen. Is it reasonable to believe that the mean mileage may be the same for both types of tread? Means for 2 different treads might be the same. Null hypothesis, mean for tread A equals mean for tread B. Alternately, it differs, not equal to. So we definitely have 2 means here. Now the question is, which type of test is it? Now, because we have 9 different cars, this is a paired t-test. Both of these first 2 numbers on the top row are related to each other. They're dependent upon each other because they come from car number 1. Maybe car number 1 has its alignment out and it pulls to the left. Maybe car number 2 needs to have, its smog check done to it. And so that might be acting on that car a little bit differently, etc. Each car might have its own little idiosyncrasies. Now, column number 1 are just labels. It doesn't get entered in there. You'd have list 1 and list 2, and this is going to be the paired t-test, which you'd have to fill in the differences into list 3 and then go do a t-test on list 3 to finish this out. Number 9. Athabasca Fishing Lodge is located on Lake Athabasca in northern Canada. In one of its recent brochures, the lodge advertises that 75% of its guests catch northern pike over 20 pounds. Wow. Suppose that last summer, 64 out of a sample of 83 guests did in fact catch northern pikes weighing over 20 pounds. Does this indicate that the proportion of guests who catch pike over 20 pounds is different from 75%? Single sample of 24 out of 83. Is this proportion different from 75%? Or is it equal to, as we have up in the null hypothesis? And since we have 1 proportion sample only, this is going to be a 1 proportion z-test. Okay, moving on to number 10. Number 10, the following table presents the number of employees by age group who were either promoted or not promoted in a sample drawn from a certain industry last year. Okay, so we have to decide, is this a matrix or is this 4 columns or is it 2 rows? Can you conclude that people in some groups are more likely to be promoted than those in other age groups? Seems like we're trying to see if there's a relationship or a dependence between the 2 categories. One of these variables is a promotional status. The other one is the age groups going across the top. This is actually a matrix, and as a matrix, it's going to be the chi-square test. Now, Here, when we do the chi-square test, and I prefer to use the word independent, dependent, or associated, not associated. I know that the associated goes down with the alternate hypothesis. And if they're more likely to be promoted from one age group, that's going to be down here. So I'm going to say age and promotional status, promo status, are, and I'm going to use the word related here. I could use the word associated or dependent if I wanted. And then above, I'd say age and the promotional status are not related. Or you could say are more likely down here. You can word it however you want, but that's logically what we are dealing with in this type of problem. The key part is noticing that it's a chi-square test. Number 11, the Pew Internet and American Life Project surveyed 2,227 adults back in 2011, asking them about their texting habits. Among men, the mean number of text messages sent per day was 40.9, and among women, it was 42.0. Assume that 1,085 men and 1,142 women were sampled, and that the standard deviations are these two numbers that you see there. Can you conclude that okay, here's my question. Can you conclude that the mean number of text message differs between men and women? Mean for the men differs than the mean for the women. Whereas alternately, or null hypothesis, mu W equals mu W. And then which test is this? This is going to be the two sample t-test. And because we're dealing with men and women who already have their genders, this is going to be a not pooled process. We are not randomly assigning people into one group or the other, because that says, oh, flip a coin, you get to be a man, or hey, flip a coin, you get to be a woman. We're not doing that. You already have what your gender is. Moving on to number 12. The Fair Isaac Corporation, which you well know as the FICO company, their credit score is used by banks and other lenders to determine whether someone is a good credit risk. Scores range from 300 to 850, with a score of 720 or more indicating that a person is a very good credit risk. An economist wants to know whether the mean FICO score, we're dealing with means, is lower than 720. She finds 100 people have a mean score of 703 with a standard deviation of 92. Okay, is the mean less than 720? That's our alternate, and the null hypothesis is that mu equals 720. Since there's a single mean here, this is a t-test. Okay, moving on to problem number 13 out of 17. A study was done to see if there's a difference between the number of sick days men and the number of sick days that women take. A random sample of 9 men found that the mean number of sick days taken was 5.5 with a standard deviation of 1.23, and a random sample of 7 women found that the mean number of days was 4.3 with a standard deviation of 1.9. At the 5% significance level, can you conclude there is a difference in the means? Okay, means of what? Men and women. Means for men differs from means of women. So that should have been pretty easy coming out of there. And then because we have 2 populations, both with means, this is going to be a 2 sample t-test. And men versus women tells us that this is again going to be not pooled. Moving on to number 14 out of 17. The compressive strength in kilopascals was measured for concrete blocks from 5 different batches of concrete, both 3 and 6 days after pouring. The data are as follows. So there you have it. Can you conclude that the mean strength after 3 days differs from the mean strength after 6 days? Ooh, mean 3 days later. I'm going to write that as mu subscript 3 differs from mu subscript 6, if that's okay with you. And my null hypothesis will be mu 3 is equal to mu 6. Now, which type of test is this? Well, notice how we're dealing with 5 different blocks. Block number 1 is tested 3 days later and 6 days later. They both go with the same block, so they are paired with respect to each other. So this is a paired t-test. We'd probably have list 1 going across and list 2 going across, and we'd have to find list 3 containing the differences. Moving on to problem number 15. A researcher claims that the mean of the salaries of elementary school teachers is greater than the mean of the salaries of secondary schools in a large school district. I'm almost wanting to just go straight down here, mu sub elementary greater than mu of secondary or high school, and mu E for elementary equals mu of secondary. Let's just make sure it's that way and finish the problem. The mean salaries of a random sample of 36 elementary school teachers is this value, and with this standard deviation, then they give us the same information for the secondary high school teachers. At a 5% significance level, can it be concluded the mean salaries is greater? Okay, we were right. That's what we're dealing with. Now, we don't have the means of pairing any data up. We do have 2 means here. So this is going to be a 2-sample t-test. Now, people already have their degrees, they already have their jobs, and we're not flipping a coin as to whether they're teaching 2nd grade versus high school. So it's pretty much an already established which group they're in. And so this is going to be a not pooled test. Moving on to 16 out of 17. In August and September 2005, Hurricanes Katrina and Rita caused extraordinary flooding in New Orleans. That was just information. You don't need the data or anything. Many homes were severely damaged or destroyed, and of those that survived, many required extensive cleaning. Still, nothing that we're going to be able to act upon for our problem. It's just giving us background information. It was I think I meant to say it was clear that, or it was found that cleaning flood damaged homes, or maybe it was thought that, I think that would be the word that I wanted there. My apology for the typo there. It was thought that cleaning flood damaged homes might present a health hazard due to the large amounts of mold in many of the homes. So here we go. In a sample of 365 residents of Orleans Parish who had participated in the cleaning of 1 or more homes, 77 had experienced symptoms of wheezing. So that's 77 out of 365. And in a sample of 179 residents who had not participated in cleaning, 23 reported wheezing symptoms. Can you conclude that the proportion of those with wheezing symptoms is greater among those who participated in the cleaning? Okay, proportion, and I'll use CL for cleaning, was greater than the proportion of not cleaning. Okay, so proportion CL equals proportion not CL, and we have a 2 proportion Z test that we are looking at here. Now, the final question that I'm going to move on to looks very scary on the screen, and I really like the problem, and we're going to go a little bit beyond just the same questions I've been asking here, just to kind of talk about it a little bit more. Here we go. Psychologists studying post-traumatic stress disorder, PTSD, often uses subjects, Vietnam veterans who were held as prisoners of war, known as POWs. Very little attention has been focused on PTSD in World War II combat veterans. The magazine or periodical Psychological Assessment back in March of 1995 published the results of World War II aviators who were captured by German forces after they were shot down. Having located a total of 239 World War II aviator POW survivors, the researcher asked each veteran to participate in a study, and 33 responded to the invitation, and each of the 33 POW survivors was administered the Minnesota Multiphasic Personality Inventory, one component of which measured level of PTSD. And note, the higher the score, the higher the level of PTSD. The aviators produced a mean PTSD score of 9 and a standard deviation of 9.32. Determine whether, okay, here's the problem, determine whether the true mean PTSD score of World War II aviators is less than 16. That's a lot, but basically they're asking, is mu less than 16? Or is mu equal to 16? And you can then see, oh, just a single mean there, this is a t-test. Now, you might have looked at this and go, whoa, all that information, why did they just go straight to this? Why do we talk about World War II and then talk about Vietnam? It sounds to me like we've got two populations here. Well, yeah, I can see why it sounds like that, because we're talking about two different wars. The purpose of the Vietnam War is there, however, because that's how they established this score of 16 that we were comparing against. But this is all about really the World War II veterans. Now, I like this problem for a couple of other reasons. First off, we can talk about sampling methods. It's so easy in this last part of the class to just say, oh, give me the data, I'm going to run a test. But quite honestly, these problems aren't any good if the sampling methods that we learned way back at the beginning of the course aren't followed. And notice how it talks about we only had 33 people responding out of 239 we contacted. So we have to look at why there was such a non-response rate. Was it hard getting in touch with them? Were they not in good health? What was the reason? And that is a chapter 1 type of question here showing up at the end of the course. The second thing I want to call to your attention, and by the way, that might have also been the voluntary response bias. Those who have the stronger opinions might be one who want to respond. The second thing is, let's take a look at the Vietnam War. Okay, it ended in approximately, I'm going to say 1972, 73-ish, somewhere in there. And this article didn't come out until 1995. So we're talking about, we're talking about 23 years later, after the war was over. Now, what were we looking at? These were Vietnam vets who were held as prisoners of war. They weren't generals. They could have just been infantrymen, and they might have, by the end of the war, I'm just going to pretend they were 22 years old. So if I were to take 22 years old and add it to that, most of these guys are about 45 years old at the time of the study, give or take a little bit. I'm just talking in round numbers. When you start looking at World War II, however, which ended in 1945, this is going to be 50 years later. Okay, so right off the bat, that might explain why we've only got these 33 respondents. But it was also that these guys were aviators, they were pilots. And even though there might be some young people flying, odds are they had to work their way up through the ranks a little bit. And they were probably, I'm going to say, 25 years at the youngest at the end of the war. And again, I'm talking in very round numbers here. So I'm going to add plus 25 in here and get 75 years old. Now, big difference in who we are studying. Those who are 45 years old, just by nature of being younger, are going to survive at a little, to be 45 years old more so. And those who have PTSD of the worst types are going to be included. But people, that extra 30 years, if they had that same level of PTSD, might have not been as fortunate to survive to get to 75 years old. And that right there might be why the mean is less than 16. So there are these extraneous things that you need to take a look at. And so I like to finish off this course while we're reviewing for which type of hypothesis test is involved to remind you that we have to blend the first half of this course with all the sampling methods and what we learned about good experimental design and use that while we are doing these hypothesis tests.